We are also joined by Marcelo Coelho. Hi, Marcelo, who is a lecturer at MIT, but at the same time, director of design at Formlabs. Thanks for being with us today.
Yeah,
we
that's my
saw
pleasure.
a couple of people, and we're just going to keep moving. So hopefully the projects will kind of like tell their own stories.
So for my project, I designed a system which generate a bowl, and by definition, a bowl is a rather deep round dish that used to hold liquids, and geometric wise, it is like cup-like hollow part container. So my design approach for this project is I first dissect the geometry of bowl into different parts, in which I imagine it has a thick base at the bottom that can hold weight, and it also consists of a rather vertical boundary to contain food within the space. And what I did is I kind of applied two different computation script correspond to the function of the two parts. So I use a lattice system to create a strong base that can hold weight. And then I use agent-based script to create a curvy surface to form the rest of the container. So start with the bottom geometry. It is designed through lattice system, which is composed of these individual units that can transit from a flat boxy unit all the way to a more rigid spherical unit that can hold compression force. And I imagine the way it can apply to the bowl is that I imagine that the top of the lattice system would be kind of a flat boxy unit, and then it will gradually transform into spherical compression unit at the bottom. And the transition of this unit can be determined by the location of attraction point and also by the input geometry. So here I create a series of iteration, then judging from criteria such as containability or how well it transits from one form to another, I start scoring them, and then I pick this iteration as the final form for the bottom geometry. Then for the upper part, agent base is applied to create a thin surface that curve upward to form the container. And here I also attempt to integrate with the base. And these are a series of iteration determined by a quality-driven process. So by looking at the detail of the shape, then I start to select parts which I think is kind of beautiful but sensible at the same time, and then I keep iterates from that. So let's say for iteration from 2 to 6, I'm interested in both showing quality of pulling on one side. And then from 7 to 12, I kind of explore another effect, which have branch come out in a radiate format. And at the end, I kind of more interest in the pulling effect, as I think it gives a sense of movement as if liquid pouring out from the bowl. And the design of that kind of manipulate the line to create density in this tear-shaped area. And also I try to create less dense vertical line to form some supporting structure for the vertical surface. These line outcomes are determined by several parameters. One of them is the slide angles for the line to be generated. So let's say if the slide angle is in Z axis, which is the vertical axis, then you create this symmetrical branching. But if it's sliding in an X and Y axis, then it will gives more a sense of flow. And then another parameter that changed the outcome is the stick value, which by determining how strong the lines stick together, it will affect how much area this dense line will cover. And the input geometry will also create different results. And as you can see, some geometry works better than other. So here I create another set of iteration to explore ways to create the ideal pooling effects. And here are some of the earlier iterations. So let's say for this one, I like the teardrop effects, but then I start to figure out how, like, ways to integrate different parts better. And then eventually I came to this, which is much more integrated, but still I'm not satisfied with the transition from solid to transparency. And then after lots of iteration, then that's kind of the final result I settle on. And this is from a top view and bottom view. So for optimization, since my bow is asymmetrical, I start looking into way to optimize the geometry to make sure the bow is stable, and also try to aiming to maximize the volume that the bow can hold. So the optimization process involves a script which can change the geometry of the bow to optimize the center of mass of this object. And by doing so, the script will calculate the current center of mass of the bow and then try to pull it as close as to the ideal center of mass by minimize the distance between the two. And on the other hand, it will calculate the volume of the bow and try to maximize it while changing the geometry. So this was the initial geometry I feed into the script, and then it starts doing a lot of iteration by changing the form of the bow. And this is the final results that it gives. And out of curiosity, I create a bow using the form the software suggests. And here I do another scoring table. And with the final iteration, create with the suggestion from optimization. But actually at the end, I picked an earlier version. Me the best geometry for functions such as volume or stability, but I cannot really create the visual effect I want from the geometry. Whereas the previous, okay, I will be quick. Whereas the previous version, I think it's visually like satisfying, and then it has a reasonable like functional score as well. And what I realized from this project is that what I encountered kind of a tension between computation optimization and visual problem. And what I found is that computation is good at optimizing functional performance, such as finding the greatest volume, shortest distance, because it can analyze data really well. But when it comes to optimizing visual quality, I found it really hard because I found it hard to describe this in a coding or data way. And I think maybe one way to approach to this is by visual computing. So here I kind of look into the iteration of both from the top view, then selecting parts I am satisfying. So let's say for this case, I like the teardrop effects. And then I start dissecting this shape into smaller fragments, analyzing how this fragment can construct a bowl, and then attempt to reconstruct the bowl design through visual computation. And I think maybe this is one way to kind of solve the problem. And yeah, thank you for listening.
I had a question. I mean, I had a question, but I think Carolyn just answered it in the last slide. It was that when you talk about, like, for example, things that you don't like visually, or for example, like it doesn't meet your aesthetic criteria or functional criteria, and then you talk about like the self-organization of like applying agents, for example, or optimization. My question was like, how do you basically use the tools, or how do you inform your tools based on those subjective criteria like that you have to actually fix what is not working? And I think, yeah, you gave the answer in the last question, but it's just my comment.
Can I jump in as well? I actually, this is beautiful. Love your work. It's super nice. I wanna have one of these at home. I guess my question, and maybe this is beyond the scope of the project, so if it is, I apologize, but I didn't hear you say a single time what this bow is for. Like, is it a bow for holding soup, or for holding fruits, or for mixing salad? Because I think that those would give you a very different sort of criteria in terms of how you optimize it, but also know how you have to deal with it, how do you fabricate it. And I think that you would have formed a really strong basis to help you resolve some of this sort of kind of just like performance optimization, but also the aesthetic ones as well. Did you have that in your mind? Did you have a specific use in mind, or not?
I don't have a specific mind at the moment, but I guess I always have an image. It's more for like fruit, those kind of things, because it at the moment it definitely cannot hold liquid. But I think that's a kind of a important like question. As in, I agree. Like maybe if I identify more specific which bowl this can hold, then I can kind of design in detail, in them like more specifically. Yeah.
Cool.
Yeah, I think it's such a neat project, and just the idea of a bowl in general, I think is really, I guess, it's a source for many artistic interpretations, and I think particularly with the sort of flowing aspect that you've incorporated reminds me of like wood turning. And I appreciate that kind of visual linkage to like how it may have spun off of a lathe or something, and it makes me wonder if there's another, rather than an additive process, like what if it was almost a hybrid of this computation plus traditional craft to generate some of these interesting designs. But very cool work.
Thank you.
One of the things I really appreciated in your design is this organic direction that these units have. And I was wondering what made you get rid of the border disc that we see. We also see it in this image. I think that for example, in some examples, you have these bifurcations end up freely, and we don't see this circle at the end, which is like a clearance. Where did you? Yes, I think that the way that you manage, the way that you handle these clearances in combination with these bifurcations in the form could help you add more functionality into this bowl, and think of handles or ways in which you could stack them together. And I think that this goes back to Marcelo's question about what the functionality of this bowl is about. For
Yeah,
example,
sorry, finish, Maroula. I was going to add something to what you were saying, but go ahead.
So for example, in this slide, the iterations that we see from 7, they almost see 7 and 8 seems like they can barely stand, whereas 9 to 12, it's obviously something that has its weight in the bottom, whereas from 1 to 5 or maybe 6, we can see how this can be a more rigid structure where weight is distributed more evenly.
Yeah, what I was going to add is it would have been great to see things like, whatever, this is for soup, let's just make that up. So that means it has to hold liquid, so then, you know, some surfaces have to be closed. But then also there's the usage part of it, where you have to say, well, you have to be able to hold the spoon, so maybe the spoon doesn't slide into the soup as you're using it, and it's kind of a different parameter optimization. That would be really interesting. And then there's another one, which is, well, do you want to be able to microwave your soup, or do you want to be able to wash it? Like all of your designs right now would be unwashable, right? Which maybe means that this is just a bowl for holding your keys when you come in at home. That's fine. I think that maybe I'm too pragmatic about things, but I find that in the end, adding as many sort of constraints that make you really grounded in reality and what the use of the object really helps you define the sort of aesthetic, and it sort of makes it very, it helps a ton. So you should take a look back at this and be like, okay, I'm gonna tweak parameters based on this one usage, and see what you end up with. I think it would be a really helpful exercise.
Yeah, I'll just add on to that comment. I think Carolyn, your comment in the beginning about the input volume kind of dictating the outcome of the final design is really important. So if you start to set up those constraints, you may find that your input volume is something completely different than what it is. I noticed you had a couple volumes that had like 2 compartments kind of dug out, which could be interesting depending on what you want that to hold. So maybe going back to that input volume and rethinking how you can construct that in a way that could be functional.
I'll jump in with just a few comments. First, I think it's a really unusual project because you picked an object which is extremely simple and you divided it into 2 parts, the bottom and the top essentially. And I wonder, like, where is she going to go with this? This is kind of crazy. But it turns out you produce some really elegant objects in the end by thinking of a bottom and the top of a bowl. And I don't normally associate bowls with grammars. I would associate bowls with parametric design. In fact, you didn't actually end up using a grammar, but that's fine. That's not a criticism. You did something different. The bottom part of the bowl is starting to be very reminiscent of woven baskets, which are optimized in many ways for structure and for function, and especially for aesthetics. I don't know if you know anything about Japanese woven artifacts, in particular bowls. So just Google that and you'll be amazed. You'll spend the day looking at these amazing, intricate objects that take, well, actually years to make when you factor in the apprentice time for the people who are making them. So the bottom part is woven. In fact, I think, in this figure, in this if they have that woven quality. And then you put the top on, the vertical part on top of that, and I thought that wouldn't work, but in fact it's kind of nice the way the top sort of sits in that nest. You kind of created a nest, which is really cool. So so all in all, I think it's really a fascinating project. I'm not sure, and I guess you haven't really thought too much, or you didn't say very much about the materials that you use. I mean, they look sort of conducive to being made of glass, so you can see the spines and the weaving. It becomes more obvious if it's made out of glass. And you also didn't say anything about scale, and that's really important to think about scale. But those are all things that you think about after you do this kind of preliminary test. You can go back and think about constraints. Your slide where you the end, the penultimate slide at the where you say that you know optimizing aesthetics is really hard. So that was a nice conclusion and something definitely good to learn. People have worked on aesthetic optimization, mostly using evolutionary algorithms and solving that problem by having people just point, I like this and I like that, and take those for the next round of, you know, the next generation of possibilities. So that's sort of one way of thinking about it. But it is kind of hard to quantify aesthetic quality. So that was a good lesson learned. So yeah, all in all, a very interesting project.
Thank you.
Okay, great. Thank you. Thank you for the feedback. And Terry, I think that was one of the goals of this class, again, trying to marry these, you know, not necessarily fully comparable ideas of computational optimization and visual aesthetics. I think Carolyn also, like, personally pushed this project a lot. The last slide is coming a little late into the process. This is the first time I'm seeing it, you know, with the, but I think idea was there because the beginning of the semester, we started with like a quick shape computation or shape calculation, if you will, and did like two-dimensional compositions, believe it or not, before we moved into, you know, 3D printing. So this is kind of like revisiting those ideas, and that question, I think, is to be discussed into the future too. So we are not kind of like solving it, but and the last point is that just to follow up with Alex's and Carolyn's projects, I'm hoping they're making it like visible that these are not only the design of the object, but it's the system design, right? So they're trying to, I think this is maybe one of the first times, is not if not the first time, for these designers to kind of like understand how we formulate this workflow or the framework for kind of like moving forward using these techniques, and kind of like jump back and forth between the, you know, the visual qualities and the performative aspects and so on.